Hello again. We are going to be addressing the last unit for this Chemistry 1C course. It is Transition Metal Chemistry. This will be chapter 19 in your textbook. Okay, what we're going to do on the first lecture is just introduce transition metals and talk a little bit about the basics, all right? And I mean a little bit. Our accent for the chapter is something called coordination compounds. If you'll remember doing the green salt laboratory back in 1B, that's what we're going to be talking about. Making those compounds, discussing what they are, why they're green colored, many different issues along that line. Anyway, we will not be talking about items such as how do you refine iron ore or copper ore into their metals. That is in another section of the book, and we just are not going to address that. Okay, so onward with the basics of transition metals. Obviously, this is a periodic table. Now, whenever we talk about the transition metals, there are several ways to consider it. We can look at these metals here in this box that I'm outlining, scandium through mercury mainly, or as transition metals, or we can look at all of these metals, including this row down here, okay? And we'll talk about naming in a minute, and also these elements down here, okay? We are going to mention them all today, just briefly, but what we will be accenting is this scandium through mercury group. Now, when we talk about transition metals, as I alluded to, we generally are talking about this block of metals, all right? Now, they fall between basically the group 2 metals and group 13. And that can be labeled a couple of different ways. As you can see here, we have, it says group 2 or 2A, and then we have 3 or 3B, okay? That means the A would be a main group element. Notice over here on top, we have A's above like fluorine and nitrogen, and the B's indicate that they are transition metals. A couple of different ways you might see that, doesn't really matter for our purposes, okay? Now, those are transition metals. We'll get into the specifics in a minute. Down here, this row, starting with 58, cerium, that is what we call a lanthanide. Lanthanide meaning it comes after lanthanum, okay? There are 14 of those. All of these metals down here in this block, the outer shell will be a D electron. Down here, the outer shell involves F electrons, both for the cerium row and the thorium row, okay? Now, these elements in the cerium row are also known as the rare earths. Turns out they're not all that rare, but they are very valuable, especially in areas like catalysis, and even more so in electronics. One of their characteristics, they all look like normal metals. They're shiny, they're hard, that type of thing. But these metals are all of a very similar size and have similar oxidation states, which makes them very difficult, or at least semi-difficult, to purify, separate. We're not going to get into those. okay? But let me just throw out a couple of examples of where you would see those, okay? One of them, as I said, is in electronics. And one area where you would see that is in certain fluorescent materials. So if you have fluorescent lights at home, there would probably be a compound of one or two of these rare earths that are included in that whitish tube. And whenever an electron hits it, it will give off a photon of a certain color, and the whole range of photons will yield white light. Okay. Another one, for example, cerium is used in petroleum refining catalysts. Okay. So when you take crude oil out of the ground and convert it to gasoline, several steps in there involve catalysts that have cerium as a component. And for the AC, the actinides, that series, you might be more familiar with those, mainly because uranium is involved and plutonium is in there, all right? And for this row, these are all radioactive elements. Obviously, uranium is of importance for energy generation. We have thermonuclear reactors, which generate power. Also, there are obviously thermonuclear weapons. Now, uranium itself is not a very healthy species in terms of you don't want it in your system, but even more unhealthy is plutonium. Uranium, once we go past that in this row, all of these elements are artificial. So every one of the elements that we have here, if we have it in our hand, or a sample in our hand, that would be a man-made species. They all have a generally, a fairly short life, but not extremely short. One of the examples other than uranium that you probably are aware of, but might not know it by name, is americium. Americium is used in smoke detectors. It gives off a radiation, fairly low level, and if there are particles in the air and it hits the particle, it will knock off an electron, which can be detected, and then your smoke alarm will go off. So americium, if you have those little pie-shaped things up on your ceiling, that is probably in there. Okay, and lastly, let's talk about what comes after actinium. Now, we have some elements here, and notice they are designated with, well, they're named here, okay? But we have never held it in our hand. These are called the ultra-heavy elements. Now, the ultra-heavy elements, in fact, this whole row has been synthesized and named. This is just an old periodic table. The difficulty with this, from a theoretical standpoint, they're great. They allow us to study them, but they are so short-lived, we don't even know what their true metallic properties are because we've never had enough of the metal in one place at one time to be able to test it. So what we do is we end up looking at the properties of the atoms and speculating. So in this row, to have a element life of like 10 to the minus third second is not uncommon. In fact, it's probably one of the longer lived ones then, okay? So again, we are going to be focusing on these three rows from scandium to zinc and then down to mercury. Now, the one thing that we do need to understand is the electronic configuration of the transition metals. When you studied chemistry 1A, you went in with the main group. That would be the beginning and the very end of the periodic table, the main part. And you would talk about the electronic structure of something like sodium fluoride. Sodium would give up an electron, fluoride would accept the electron, you form sodium fluoride, and you have a salt. Both materials or both ions have an octet, correct? Meaning what? Meaning that sodium gives up that electron to form an octet. Fluoride completes its octet, right? You remember that, I hope. Well, with the transition metals, there are 10 electrons possible in 5d orbitals, which means that we probably are not going to have an octet or a filled shell very often. I say octet to mean a filled shell, okay? Now, if we look at the first row of transition metals, so you might want to pull out a periodic table, what you will see is for scandium, we filled the 4s electrons, okay? Why did they come first? Because the 4s level is lower, more stable than the 3d orbital, okay? Now, whenever we put 2 electrons in, we have the equivalent of what? A calcium electron, right? If we add one more, that extra electron comes up into another level, and that now becomes scandium, all right? So as we go down, what happens? We have calcium here, essentially, and as we add electrons, we add what? Obviously an electron, and we add a proton to the nucleus. So the nucleus is getting larger, and it's pulling the electrons down, meaning it is shrinking the size of the atom, which is what we talked about happening in the main group as well, correct? So as we come down, if you have 2 electrons in the calcium s orbital, and you have now a mounting number, an increasing number of electrons in the 3d orbitals, what's being pulled on more? Well, the 3d orbitals, because you have more electrons. So eventually what happens is that, let me put this up here, what happens is the electrons in the d orbital fall below those of the s orbital and become more stable. So now, at some point, the calcium electrons are the outermost electrons, okay? So when you're reading over the chapter, keep that in mind. And that will make a difference to us whenever we go to determine or try to determine the electron configuration of an atom versus an ion for transition metals. Okay, so we started with scandium. If we go to titanium, well, that's 1 over, so that would be 1 extra electron. So we put in a second electron. And what did we find happens whenever we have partially filled shells, like the p orbitals? The first thing that happens is the electrons go in singly before they try to pair up. Why? Because they don't want to repulse each other. If they can minimize that repulsion, that will be a more stable configuration. So let's look at what happens. We go to 2 electrons, obviously, those should be unpaired in the d orbital. We go to vanadium, we have 3 electrons, and those are unpaired. Now look what happens with chromium. Chromium is kind of an odd one, isn't it? We went from 3 to 5 unpaired electrons in the d orbital. Why would that be? Well, if we have 4 electrons here, and then we add a 5th what we would have is 2 electrons that are paired in the chromium, or, well, yeah, 2 electrons paired from the calcium backbone. And then we would have 4 electrons here. But what happens is somewhere in here, remember I said that the d orbitals drop below the s orbital? That happens. And when that happens, the more stable configuration is where they are all unpaired, because it minimizes the energy of the atom, the overall electron configuration of the atom. All right? Now, once that occurs, then we move on to manganese. Well, we have no choice but to pair up again. So we have 2 electrons in the S, 5 unpaired in the D, and then we continue on with iron, cobalt, nickel, adding an electron. And now we have to pair up, right? Now look what happens with copper. If we add an electron to nickel, it would come here and give us 9 electrons normally, we would think, in the d orbital. But it turns out that the more stable d orbital is completely filled versus the d orbital with 1 unpaired spin. So as a result, one of the electrons goes from the copper to the d orbital, a d orbital, and we end up with an unpaired spin on copper for the metal. Then, of course, to finish it out, we are looking at zinc, and that would give us the filled shell. 2 in the S, 10 in the D. Now, when we talk about the transition metals, let's talk about what we mean by a filled shell. We can mean 2 things. We just got done talking about a filling of the d orbital, so we can talk about a filled d orbital set, right? What we can also talk about are the number of electrons we required to give us a complete shell across the periodic table. Look at your periodic table. You have potassium and calcium as the S. You have these 10 metals, the transition metals, so you have 10 extra electrons, so that's 12. And then if we look past zinc, we are looking at what? We are looking at gallium through krypton, okay? So that adds an extra 6 electrons. So 12 and 6 is 18. So when we talk about a completely filled shell with transition metals, we're talking about an 18 electron system. And we will see later when we talk about or get into the complex ions or coordination complexes, why that is important. Okay, now, before we move on, let's talk about how we determine electron configurations for the atoms and ions, compare them. Now, we talked about the atoms, and this is the first transition row, okay? It's the 3 d orbitals, but it's the first row of transition metals, okay? Now, what we're going to talk about with respect to electron configuration, as you go down the periodic table, let's go back up to it, what we just got done talking about for scandium through zinc holds. All of our assumptions hold as we go down the periodic table. So the electron configuration for yttrium, lanthanum, or nickel, palladium, and platinum would be the same as the first row, okay? All right, that applies to the atoms, the free atoms, and the ions that we would predict, the free ions, okay? Once we put other stuff around them, it may no longer hold. okay? But that's our starting point. Okay, now, if we look at something like, let's take titanium since that's our example, and we want to know what titanium plus 2, what that electron configuration would look like. What would we see? Well, we look over here at titanium for the row, and these are all of the outer electrons. That's all we need to worry about, right? Now, we have 2 s electrons and 2 d electrons. Now, if you remember, I said as the electrons are removed or added, they will add to the d orbital, and that d orbital drops because of the protons, right? Okay, what that does, in effect, whenever we put them in, we generally put them in the d orbital, but when we take them out, we start with the s orbital. So here for titanium, the first 2 electrons we would take to get to titanium 2 plus would be the 2 s orbitals at ligands. Meaning, what do we have left? Only the 2 d orbitals, right? So that would be a D2 configuration, D superscript 2, to indicate 2 electrons in a d orbital. Okay, so let's look at a couple other options here. If we have zinc, all right, or zirconium, say. No, let's say zinc. If we have zinc, what would that electron configuration be? If we were to write it down for zinc, it would be 4s2 5d 10. And if we said, okay, for zinc plus 2, we remove 2 electrons, so what would that be? We take 2 out of the s orbital, so it would be 4s0, superscript 0, 3d 10, okay? If we have, and we're just going to cherry pick here, if we have palladium plus 4, okay, so let's see what happens here. Let's go back up to the periodic table. Palladium. Well, palladium obviously is not in the first row. So what do we do here? We look at palladium and we say, all right, how many electrons do we have there? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons total. So if we have, that would be what? 4s2, or no, excuse me, 5s2, 4d what? 1, 2, 3, 4, 5, 6, 7, 8, right? Okay. Now, what did we say the charge was? Plus 4. Okay, so what do we have? We take out what first? The s orbital electron. So we take 2 of those, and then we need to take more away, so we take 2 out of the d orbitals now, right? So that would leave us with what? An S0 D 1, 2, 3, 4, 5, 6 configuration. Okay? It's not hard, just getting used to. Okay? Now, I'm not going to do any more here, and the answers are down here. Okay? For the rest of them, if you want to play with that. They're not hard once you see it, and actually, maybe most of you have already had that in chemistry 1A. That is sometimes covered there. Okay, now let's talk about oxidation states. And it turns out there are some oxidation states that are more common than others because they lead to more stable ions or compounds later whenever they combine with other species. And all I want to do here is point out 2 things. One, what are the most common oxidation states, we are only going to be really concerned with those. And then what are the less common ones, and how can they form compounds? Well, it turns out, let me address that right now. When you look at something like some of these green oxidation states, they are very high or very low, and their compounds that they form, or the species they form, are reactive. So, for example, you may form a compound with, let's see here, what would be a good example here? Maybe chromium 1, okay? That's unstable, it wants to be reactive. So what you may end up having to do is, if you're going to make a compound with chromium 1, it has to be under conditions where that species cannot react. So let's say that whatever we're making reacts with oxygen. So the simple answer would be, if you're going to synthesize it, you synthesize that material in a non-oxygen or oxygen-free atmosphere. Maybe nitrogen, maybe argon, neon, something like that, okay? But we're not going to really worry about those. Just be aware that they exist. Okay, so if we look at the most common states, well, let's start with scandium. If we look at scandium, that state would be +3. And what does that mean? That means we are taking the d electron out and the 2 electrons on the s orbital. If we look at zinc, the most common state is +2. What have we taken out? The 2 s electrons. And one way to think of it is we're leaving the 10 d electrons because they're a filled shell. You have to add extra energy then to peel out an electron from a filled shell. Let's look at iron. If you'll remember from what you've studied in the past, you probably mainly came up or were exposed to iron +2 and iron +3. Okay? Now, those are, and we'll see why later, they are the most common oxidation states. All right? But they are the ones that form the simplest oxides, the simplest chlorides, any of the salts, okay? Now, that is the first group, transition metals. Notice that as we go down the periodic table to the second and third row, that these transition metals are more likely to go to higher oxidation states, okay? There's not as many filled items up here as there are here. Why? Well, as you go down the periodic table, you go from a smaller atom or ion to a little larger, and then maybe just a little larger, but you're adding whole rows of electrons. So it is easier as we go down the periodic table for those electrons to be lost and form oxidation states that would be tougher to form when the ion is smaller and the nucleus pulls the electrons more tightly, okay? Now let's talk about transition metal complex color, or metal color in general. If we look at transition metals that we've dealt with, and go back to your green salt, that was a really nice compound that you made, kind of an emerald green, and I can't think of anything in the main group, the sodium chloride type compounds, that was highly colored. I can think of some ones that were like yellowish, but no greens, blues, oranges. But let's go back to the green salt. What did you do in that experiment? Well, you made the green salt whenever you added oxalate. And then if you'll remember, when you changed that oxalate. Well, I basically analyzed it for iron. You decompose the oxalate, the green compound, and added a nitrogen ligand. I think it was orthophenanthroline. Probably don't know what it looks like, no big deal. And what happened there? You got an orange complex. And depending on how concentrated it was, it looked a little bit like an orange crushed soda without the carbonation. Very pretty. Why do they form the colors? Well, we're going to talk about that very simply here, but one of the things we would like to be able to do is to say, here's what the compound I made. I predict it will have certain characteristics, like it will be magnetic or non-magnetic, it will have color, no color, and if it is colored, what color would it be? Okay, so let's talk and compare just very briefly the main group and the transition metals. If we look at the main group, we're talking about electrons being exchanged between s and p orbitals. And those are fairly far apart. Now, if you have an s orbital, say, that's jumping to a p orbital or something below the next level down, if your s orbital's empty and jumping up, you have a large energy gap to go through. Now, the higher the energy gap for an electron to jump up means what? It takes a lot of energy, right? Small gaps require small energy, big gaps require big amounts of energy, and it turns out the energy that's required for the main group elements is usually in the UV range, and we can't see UV. So as a result, these compounds appear colorless. If we could see UV, would they look colored? Yeah, depending on what sensing organ we had or mechanism. Now, if we have transition metals and we see color, what does that mean? That means that that energy, if UV requires this much energy to jump, and for visible, we only require this much energy, lower amount of energy, and it turns out the visible light just happens to be in the range in which these s to d orbitals or between d orbitals where those electrons can jump. Now, we're not going to worry about where it's jumping from or where to at this time. All we're going to worry about is, can we see it or can we not, the transition. And what we're saying is for transition metals, we can see it. It is a characteristic that is useful to us, okay? If we take two examples, calcium, like calcium carbonate, and manganese 2 carbonate, if we look at the electronic levels, notice here we have for calcium a 3s 3p filled shell. Okay. Now, why do I say that's a filled shell? Because calcium should be what? It should have 4s2 electrons, which it doesn't. So the only electrons or the highest energy electrons it has is the next row back, which would be the 3p6. Okay. Now, if we look at the characteristics of that compound, we find it is not colored. If it is in solution, it looks clear, colorless. If it's in a solid, it will appear to be white, and it is what we call paramagnetic. If we take a magnet, it won't do anything. There's no unpaired spins. However, if we look at the manganese carbonate, it is a partially filled D shell, which means we should have what? Unpaired spins. And it turns out that that is what we call dimagnetic, meaning if we have a magnet here and a sample here, that sample should be attracted to the magnet, and also that compound would be colored. Okay? Now, whenever we talk about what we talked about, magnetism already, that last slide, and again, we're just repeating sort of the last example. Calcium sulfate, both ways, and again, white non-magnetic. And for cobalt, instead of the manganese, it's red and paramagnetic. Okay? Now, that is the end of the introductory lecture. What I would encourage you to do is read this portion of your textbook, the portion talking about the properties of transition metals in general. Accent what we discussed on the slides, but also pay some attention to the other trends. They are useful in sort of a peripheral way, okay? You probably won't see anything on the test except maybe lanthanide contraction. You might want to look at that term. We didn't talk about it here. It's a fairly simple concept. Just be aware of it, okay? So next time what we will talk about, we will introduce coordination compounds, okay? They are compounds you can loosely think of as the next step of complexity. You have simple compounds like iron oxide, rust, and then you have the next level, which would be your green salt type complexes, and that's where you get the 18 electron shell and try to fill it and make stable compounds. Don't worry about it now. We'll talk about that, introduce it next lecture. Okay? Have fun reading.